Okay, and yeah, we have pretty good quorum, so we can get started. Okay, welcome to the AQT seminar. It is my pleasure to introduce David Ferguson from Northrop Grumman. David is quite good device physicist and physicist in general, and also a good friend of mine. He did his PhD at University of Illinois Urbana-Champaign, and in there he did a lot of work on hard condensed matter physics, different aspects of unconventional superconductivity. And after that, he has been working on superconducting device physics and different aspects of quantum computing with superconducting systems, at first as a postdoc at Northwestern University, and since about, I don't know, 7 to 8 years ago at Northrop Grumman, where he was the quantum device theory team lead for a few years. And he co-invented a few different devices and theoretical and numerical methods to model devices and experiments. And he's currently the principal investigator of the Silver Bullet program, who's a program that's comprised of many institutions to develop noise-protected qubits. So without further ado, I'll just leave it to David. Take it away, David. But before, let me tell people, don't be shy about questions. Interrupt anytime. David likes his talks to be dynamic with back and forth, etc.
Yes, I certainly do. It's a pleasure to be here. I will say one thing that I don't even know whether David knows, but at my time at Northwestern, of course, they have a great research program into superfluid helium-3. And so that is a definite passion of mine. So if you get bored, if you're ever in a conversation with me and you get bored about talking about superconducting qubits, don't forget to bring up helium-3. I love helium-3.
So we can talk about weird topological excitations.
Exactly. All right. Let's make sure we go. Okay. So I'd like to begin by thanking the funding agency for the Silver Bullet program, where most of the results of this that I'll talk about, at least the experimental ones that at Northrop Grumman were funded by, and all of these great university teammates that we collaborated with on this work. And just one second, hold on, apologize. Got it. And of course, Northrop Grumman is a
David,
yes.
Can you share your slides?
Oh, they're not. I'm not sharing my slides. I thought I was. Thank you, Monica. How about now?
Yes, now it's on.
All right. And I'd like to thank my Northrop Grumman colleagues. Previously worked with David there, so he certainly can tell you what it's like to work there as well. In my view, it's a great place to work, and I've learned a tremendous amount working there. A lot of great colleagues there. And of course, this is a big field. Lot of interesting teams, even other than our collaborators, that is doing spectacular work. I think that's a bright future. So first, I want to kind of tell you a little bit about just some of the background of Northrop Grumman. We do a lot of development of superconducting compute technologies within our transformational computing division. And we have team in Baltimore, Maryland, as well as Denver, Colorado. And we kind of work on the full range of stuff from design and fab and test and theory. And here are some kind of just some eye candy about some of the stuff we do, some stuff more on the classical side, novel qubits, and even some stuff in quantum annealing, quantum optimization, machine learning. One of the fun things that people may not know about Northrop Grumman is we got, of course, over the years have been formed out of many different companies, but my division comes out of Westinghouse, and Zener of the Landau-Zener formula was actually the director of science at Westinghouse. So you'll see later on in the talk, this Landau-Zener formula, or these kind of Landau-Zener concepts, are a key part of what we view as the whole protected qubit framework. And it's fun to think about that you're trying to live up to this legacy that was just kind of blazed before you. So
didn't Westinghouse develop some of the very first commercial squids?
I'm not sure about about squids. I definitely know about transistors, and actually this on the Northrop side, not the go ahead.
Well, I don't know if it was true or not, but the squid thing, Fusco told me that.
If Fusco told you, it's definitely true. I will say, one time I was in the Computer History Museum there in Mountain View, California, and I got to see in person one of the very first digital computers that was developed by Northrop. One of the first computer. It was a hybrid analog digital computer, and so it's fun to kind of look at that and imagine, modern quantum devices where people are aspiring to be hybrid analog digital devices, and just kind of think about those early devices. So the overall outline here, I think perhaps we'll see what we can get to. Going to talk a bit about just kind of some of the basic concepts, some of the key ideas that I kind of latch onto when I'm thinking about things. A really fun idea that was developed by my colleague Ryan Epstein here at Northrop Grumman, that kind of is a kind of stitching together of some of these ideas into a specific concept, and you can kind of see illustrated in real device physics some of the concepts that I'll talk about in abstract. Talk about some of the properties of the current mirror qubits that we have been developing experimentally at Northrop Grumman, and just kind of touch on, hopefully I'll have some moments to touch on some of the outstanding university research that I think is particularly exciting. So one of the things that I think is important to say is that there's a tremendous amount that's going on in the NISQ era, but including dramatic improvements in coherence times and et cetera. But at a fundamental level, all of these qubit types are linearly sensitive to noise. So basically, the thing that you can do is you can make the environment quiet, but beyond that, there's not much else that you have to do in design. Whereas that's not, if you ask the question, is that theoretically necessary? Does your qubit design have to be linearly sensitive to noise? And the answer is no, it doesn't. But what would have to change about the kind of the base Hamiltonian that you have in these kind of NISQ systems? And the primary thing that would need to be changed is that these qubit terms, these single qubit fields, are the dominant terms in the Hamiltonian that kind of set the large energy scale for the frequencies of your devices. And then the kind of the interactions are much weaker, and you use them to kind of do gates between devices. But one way that you can kind of stand this thing on its head, and to design qubits that don't have this property, that they're linearly sensitive to noise, is by making the interactions between qubits much larger than the single qubit fields themselves. And that kind of general kind of reorganization of the structure of the Hamiltonian is one of the critical things that, if you're going to say, well, in theory, does it have to be like this? And the answer is no. There are options that are in our toolkit.
But if you make your interactions the dominant energy scale, how do you keep information local?
So you would need mechanisms to so one thing I will say that certainly for instance, here's this nice 3x3 grid. The quantum information is definitely spread out across these 9 qubits. But of course, you would then need mechanisms to make sure that you could still prepare and read out and then do gates between these between such protected qubits. And I'll kind of touch on during the presentation, a way using those adiabatic concepts of kind of deforming these codes that allow you to do gates, at least Clifford gates. Great. So here's the kind of the general concept, and it's kind of in some ways straightforward. So of course, a lot of things that people are trying to do is they want to do gates, and they want to do error correction, and a lot of times that amounts to measuring various stabilizers of codes. So instead of an approach where you are, getting this information through gates and readout of ancillas, instead what you can do is you can, basically just build a Hamiltonian where you just do some sort of sum over all of those stabilizer generators of your code, and then you generically find that you get a qubit subspace that is kind of separated from leakage states. And in particular, if you then start acting with noise locally, it doesn't decohere you. So over here, I've shown just a kind of a very basic plot, the following numerical study, where you basically take this kind of Bacon-Shor code terms, and then you add in various just kind of random perturbations of random polyoperators acting on all of these sites. And of course, if you have just a single qubit, that of course there is no error suppressing terms, and you just get that same RMS noise in your physical qubit. But as you go ahead.
For this idea to work, is it important that it be in a subsystem code like Bacon-Shor? It wouldn't work for a regular subsystem code or something like. It wouldn't work for something that needs like decoding.
So what I would say is we'd have to kind of discuss through the specific cases. I would say that I imagine that there could be additional complexities of how you might want to do gates, for instance, if your system got too complicated. But it's an interesting question as to what type of which approaches would be most amenable. I like the Bacon-Shor case, of course, because in that case things are a sum over 2-body operators instead of like 4-body operators, and of course it's much easier to imagine engineering 2-body interactions than 4-body or higher.
Yes, low parity checks. Yeah.
Yes, exactly. But just to come back to the narrative of what these few dots on this graph mean, it just means that as you kind of expand yourself to kind of larger and larger code sizes, 2x2, 3x3, 4x4, you find that the errors, the kind of the noise that gets transferred into your qubit subspace gets suppressed dramatically by this kind of very large exponential factor. So that, down here, you're talking about noise that's, sub on the Hertz level, kind of human perceivable frequencies. All right. So, of course, I think that it's also important to mention that these type of kind of based ideas are not the only ones that are there. There are an important class that comes from this kind of this kind of famous GKP work here, where the stabilizers are not formed out of direct Pauli operators, but in fact about displacement operators. And the key physics there is that you need the displacement operators if you kind of to basically trace out a area in phase space that can encode two states. And in that case, if these are the dominant terms of your Hamiltonian, you then encode a qubit in these so-called GKP code states. And of course, this is something that is extensively developed at Yale in terms of the states themselves. But I'm saying that instead of using some sort of elaborate control technique to generate these states, you can instead just kind of somehow engineer these terms in a Hamiltonian, and then the ground states of your system become the way that you generate these states. So I thought maybe I was getting a little bit of internet jitter. Am I still good, David?
Yeah, at least on my end, I can hear you fine.
Okay, great. So similarly, as you kind of add in this kind of random noise here that couples into your say phase and charge operators, or maybe to your excitation number of these variables, you add in these perturbations again as you change the relative energy scale between these kind of local terms that are just kind of comprised of derivatives and etc. The normal kind of in the normal terms of your Hamiltonian here, of your kind of a harmonic Hamiltonian, again you kind of get this exponential suppression of local of noise coupling into your qubit system. So an additional variation on this idea is ideas where instead of having just a conventional 2D phase space of of position and momentum, say, or charge and flux, you have a periodic variable like you get when you have quantized charge in a superconducting circuit, and then there you can get very similar ideas where what you need in that case is the ability to exponentially suppress any sort of single charge or single vortex hopping, but you need to have large double hopping or so-called parity hopping. So I call this a parity valve, because you kind of need some way to turn on two Cooper pair hopping. So this is a nice inspirational ideas as to that, yeah, if you there are better things that we can do. If somebody some experimentalist comes to you and says, oh man, I want something dramatically better, something that gets exponentially better. Something that would be like a quantum transistor, it's totally fine, totally coherent. You have these ideas in the back of your mind as to theoretical ways you could go, but if you're kind of dealing with at least a superconducting system, those kind of things that you would want to have aren't necessarily the things that you do have. And of course, what you do have is still pretty extraordinary. So anything that you can kind of draw with inductors and capacitors and Josephson junctions, can basically be made. And so the toolbox, the design space, the creative space that you have is really exciting. And there are just some sort of rules as to, when you look at this type of thing, how many conserved charges you have, how many periodic variables you have, how many kind of real variables you have. And there's kind of, we've spent a lot of time developing these type of simulation tools at Northrop Grumman, and we're really at a stage where you can really just, plop something down and see what it does in design, and that's a super exciting place to be. One other key thing is a lot of times when you are thinking of these type of circuits, it's intuitive to think, Oh, right. I have charges that can hop across junctions, or charge that can slosh back and forth across inductors. But one other intuitive way of thinking is, instead of thinking about how charge moves through your circuit, you can also think about how, when you have superconducting loops, you can kind of think about how, vortices, for lack of a better term. I'm not talking about things with a vortex core inside of a piece of superconductor, but just a winding of your superconducting phase around this loop. But that can kind of change by discrete amounts as kind of your winding changes, and you can kind of think about that as a vortex entering or leaving this loop. And we've developed, in collaboration with Northwestern, some very nice tools that allow you to kind of think about these circuits from a flux dual perspective. And that really kind of, again, opens up the design space where, where certain things would have been hard in, thinking about things in terms of charges hopping around, become easier when you're thinking about vortices hopping around. In particular, by putting in some very clever Mobius capacitances, which come from an original work from Kitaev, you can actually exponentially suppress single vortex flips out of this loop, but you can have very strong double vortex hopping out of this loop. And you apply this procedure to this complicated circuit using our awesome tools, and you actually see that, yeah, in this kind of low energy subspace, this kind of checkerboard Hamiltonian, which tells you, okay, you have some inductive terms along the diagonal that describe how you get more, that you get more energy cost as you kind of go to higher currents around this loop. But then you see that the transitions that you get conserve parity, that you get 0 to vortex state to 2 to 4, but not 0 to 1, as would be conventional, say, in Fluxonium. Another key thing that I think is important to think about, and certainly would be, one of the things I was talking about, David, before this is, how bummed I was not to be there in person, and things that we could talk about if we had it, what reasons we could have to potentially have a visit in person at a later date. And I do think that while gate motivated approaches are really exciting, but so are analog ideas. Kind of what you would do to build an analog quantum simulator is very exciting ideas. And in particular, how might you generalize? So in this case, in some ways you can kind of think of quantum annealers like D-Waves as a version of a quantum simulator. And they're doing a lot of great work in terms, simulating the KT transition. A lot of great works coming out of their quantum simulation in D-Wave. But what would you need, and to not just have current ZZ interactions in the system, but to allow more general type of interactions, like XX interactions or YY interactions in these type of superconducting systems, and in particular in these kind of flux qubit type systems. And this work by Jamie Kerman really kind of shows, unfortunately, you kind of do need some to get into a regime where you have some charge biasing, but you do have this kind of ability to, in fact, have arbitrary poly operators X, Y, X and Z, and even in a generalized design, poly Y operators all be current in character. So all that you would then need to do is have a nice way of making current interactions and be able to choose the ones that you want. But in that way, you can get a very exciting idea of how to get an arbitrary poly analog quantum simulator, which would be a very powerful device.
Does the control hardware overhead grow a lot by trying to implement all of this?
I would say that the calibration definitely would be extensive, but not different from D-Wave. Maybe maybe you'd need twice as much ability to tune things up as D-Wave has. But once you kind of set DC levels, you could have some sort of global bias line that that then says, okay, go forth and anneal type of thing, like is done in D-Wave. So one of the projects that we actually, oh, sorry about the dog barking in the background. One of the things that we've been working on at Northrop Grumman is a high coherence and much higher degree of control a quantum annealer that we've developed in collaboration with Lincoln Lab, and we have actually tested out ideas like this. And we not only saw the ability to anneal it like you can a standard annealing qubit, but we also began to see evidence that we could get this type of what's so-called non-stochastic activity or non-stochastic behavior for these type of circuits. So so I would say that one of the key things to emphasize is that there are it is kind of known how you could make actual two-level qubit poly-level systems in these superconducting qubit systems, and how you get all these interactions, but there can be significant experimental challenges. For instance, calibrating offset charge. Almost every single qubit these days has gotten rid of DC sensitivity to offset charge, and you might need to build that back in. So there would be new challenges, but it is kind of known, and that's exciting that you kind of have that ability to kind of tap into these ideas.
Yeah, but building it back in makes you more sensitive to charge noise too.
So it would be one of those things where you would have to take, if you're going to do things with this route, and there are other routes, of course, but if you were going to do things with this route, you'd have to take one step back to then take steps forward. So, if you kind of, it is a distinct possibility that you would have to kind of like say, okay, you go back up to here, the thing that's in this corner is not a great qubit. It's very different from a transmon or a fluxonium, but it has the right knobs so that it can then be put within this type of framework. So that's one option. I'm not saying it has to be like that, but that kind of one step backwards so that you can actually make dramatic progress forward is definitely one of the possibilities of what this technology is telling us. Okay, so let me tell you about a different idea. This one kind of gets around this kind of charge sensitivity issue. And it's based on fluxonium qubits, which is one of the more exciting qubits out there. It's not a protected qubit. It doesn't do noise suppression, but it linearly feels noise in a much different way than a transmon does, and so it is quite an exciting qubit to think about. So here is a variant of a fluxonium qubit. And one of the things that it has is not very large circulating currents in this loop because the loop inductance is huge. But this is a kind of a large bump, what I call a large bump fluxonium. And so the actual kind of hybridization that you get between a state that's in your left well and your right well, say, is minimal. Okay, so that's kind of the regime that I'm going to be kind of imagining engineering into. And for the moment, so one thing that you get in that type of qubit, it becomes a very noise asymmetric qubit. Okay, so it is very it's sensitive to flux noise. Any sort of flux noise kind of it's linear sensitive to, but it is not sensitive at all to bit flips, X noise or Y noise. You can't very easily at all make a transition from this well to this well, and it's T1, is basically effectively, as long as you want to make it. All right, and so if you had this type of asymmetric noise and you wanted to add something on top of it, what might you want to do if you really want to kind of extend this even to kind of even suppress that Z sensitivity and give you some ability to do gates? So one thing you might want to do is have a mythical, and I'll explain how we imagine this might happen, But for now, a mythical XX coupling between these type of this noise biased qubits, has this dramatic difference in the way that noise affects this qubit. And if you have this type of chain of XX coupled qubits, then what you see is that what's nice about this is that you get a large gap between your kind of doubly degenerate computational states, and here it happens to have the lowest leakage state is also multiply degenerate, but the gap does not shrink as the code size increases, which is one of the things you got to look out for as you're kind of imagining how these things could be engineered. However, the nice part here is that as you get to longer and longer chains, again, your sensitivity to noise, not only does it go down to in an absolute scale, but it's now suppressed to higher and higher polynomial suppression in that kind of length of the chain. And this gap energy, of course, you do worry about these type of excitations up into these leakage states. But if you make that gap big enough compared to, you say, your thermal energy, then that's another exponential suppression that you can get in terms of how much excitations you get up into those leakage levels. So let me just kind of walk you through this diagram a little bit. It kind of gives you, and some, this is the type of thing that we like to look at, where in some ways I like to think of this as, my favorite type of equation. Because it is a device schematic, but it encodes how you would build up a Hilbert space and all of the steps that you need to kind of understand what the physics of this device is. So let me tell you a little bit about what this device is. We're kind of imagining it again. It's this kind of these fluxonium loops, but we have it set up so that in this case you have a small shunt capacitance, and so that you get very strong tunneling out of this loop across this junction, kind of if you're in the Blochnium regime, you might say, but you also have very large shunt capacitances, so that it also becomes highly localized in certain directions, and those certain directions are in turn highly correlated with the neighboring device. And because of that, what you get is highly correlated bit flip behavior. And in particular, if you look at the structure of what things are happening inside of this kind of low energy subspace, you see that this device turns on a strong XX coupling between these two lowest energy states of the fluxonium itself. So the single qubit X is suppressed. You don't get any single vortex hopping, but in contrast, you get this large double vortex hopping. Unfortunately, there is a design challenge here. You simultaneously want extremely small shunt capacitances. We're talking hundreds of attofarads, and very large shunt capacitances. 100 or more femtofarads. And even so, you're not quite in a regime where your energy scales are large compared to your thermal energy. So this one it's not quite ready for prime time, but it is an inspiration to kind of see that these components are compatible with this type of error suppressing physics. Another key thing that is generally true of these approaches is that when you turn on interactions, so here we have qubit 1 up here in this chain, and you have qubit 2 down here in this chain. When you turn on these kind of interactions, say between an edge, they don't turn on like a standard logical operator. It's much more complex than that. And in fact, you kind of get the same sort of you get this same type of power law suppression. So when you have very weak coupling, the coupling between the actual qubit variables is itself very weak. But then, as you kind of ramp on these couplings, it then kind of turns on in this very nice kind of nonlinear, kind of almost digital way. And so that type of ability to turn on, your couplings, in a not very well controlled way, and get a very well controlled behavior on the coupling between your qubit subspace. That is a very nice feature.
The solids are theoretical curves and the dots are simulation.
That's right. That's right. Mm-hmm.
And the sort of leveling off of the simulation, that's a numerical artifact.
Over here?
Yep.
No, that's real. I mean,
That's
eventually,
real. Okay.
yes. Yeah, when these energy scales of ZZ get comparable to your XX coupling,
Okay.
Other stuff happens.
I understand.
Yeah. So getting back to old Zener, what is it that you can do in order to now do, say, a controlled NOT gate between these type of qubits? So here is a length 3 chain. Here's another length 3 chain, and here is another kind of length 3 chain, but it's got these these single qubit terms on that are kind of biasing it, and so it's not even this is don't have any quantum information stored there. You just have a single kind of ground state space of this device, this area. But what you can do is you can kind of adiabatically turn off those Z bias and adiabatically turn on this XX coupling here, and kind of grow this chain. And then in turn, what you do is you then kind of turn on the interactions between this part and turn off this X coupling here. Again, all these terms you see in the Hamiltonian, you can imagine them. Anything that's different between 2 and 3, you imagine this term turning off while this one is turning on. And then you do this kind of neat trick when you're turning this one off for the final time. Instead of kind of being Z biased, it's X biased. And when you see what the effect is on the computational subspace, you see that you've actually implemented a controlled NOT operation. And between these two qubits. And so these type of adiabatic gates actually give you allow you to do this kind of critical entangling gate between these error suppressing qubits. So just because you're immune to environmental noise doesn't mean you can't make these guys strongly interact with each other. And you can actually make them interact in a very well-controlled way. So this is from an earlier work, again by my colleague Ryan Epstein, and he was kind of studying these type of adiabatic gates where you're kind of turning on these terms. And what you see, it has this really nice behavior that even if you have these kind of very noisy pulses, as long as the next guy over is turning on, while this one is turning off, you just kind of have an overlap between your pulses. You can get these very high fidelity gates. So let me just kind of walk you through this kind of diagram. So I'll just focus on these kind of blue dots here. So this is this type of gate protocol, that I described on the previous slide. And as this kind of gate time gets longer, it kind of gets more and more into this adiabatic regime. And here you're doing a 10 to the minus 5 gate. You can, of course, just take, 2 qubits, turn on a ZZ interaction between them, and correct the right rotational phase and get a high fidelity gate, for instance. But as soon as you get any sort of noise, as soon as you kind of, take your whatever pulses that you did to kind of get the right area for your kind of whatever pi/2 rotation, and then you kind of add noise on top of that, whatever you've tuned up here becomes these black dots. And so no matter what your gate time is in this type of kind of basic scenario that everybody does their gates by just kind of like, not everybody, but the most standard gates in this NISQ era is just kind of like you wait for the area to be the phase that you want. When you get this noise, you're just out of luck. However, if you're doing things with this adiabatic approach within this error suppressing mechanism, you not only do you get this kind of resilience to environmental noise, but you get resilience to control noise as well. So this is, you kind of everything's looking great. All right, so I'm going to go rather quickly, David, maybe about, what do you think, 5 more minutes talking about current mirrors and what we've gotten there?
Do 5 to 7 and then we'll take questions.
All right, perfect. So let me tell you a little bit about the qubit type that we've been exploring experimentally at Northrop Grumman. Again, it's this kind of current mirror. It's designed to get this vortex parity protection. It has this kind of in its reduced low energy description, it has this kind of parity valve. And we've hooked up this novel readout technique that was actually developed in our quantum annealing program, where it's kind of demonstrated there. It basically, what it allows is this device basically senses how much circulating current is in this loop, and it kind of uses that information to modulate a tunable resonator. So let me basically go right to the data. It'll be a little bit, well, actually not quite to the data yet. So let me tell you a little bit more about this readout. So as you kind of sweep the amount of bias that this kind of QFP, it has like one knob. Okay, so I told you that it senses how much current is flowing in here, but it also, if you kind of bias it with some sort of external source of flux, you can. That's also a way to kind of turn on some sort of sensing of this QFP. And what happens is that it takes one part signal from your qubit, one part signal from that bias line, and it does its kind of quantum annealing thing. Essentially, it functions basically how an annealing qubit works, and it kind of turns that kind of sensing information into a much larger current. It kind of amplifies that signal into its own circulating current that again biases this resonator that you can then kind of probe with, for instance, microwaves. So what you get is I'm going to focus on this dotted blue line here for a second. Imagine that it's not coupled at all to this current mirror. It just has your regular delta, we call it a delta bias into this QFP. As you have a very low delta bias, you end up with one circulating current of this QFP at the end of the readout, and then you get one signal. The probability to observe that kind of say left circulating current of your QFP is very, very, very low. You get right all the time, but then as you kind of ramp that delta bias, that kind of flux bias to that QFP, it changes to the to very high to the other circulating current, and once you then kind of plug your qubit that you're interested in onto the end of that QFP, whether that qubit stays in one of its circulating currents, it'll shift it, one direction and the other direction. And when you're in this regime, if you bias into this regime, you get this nice discrimination that tells you the state of your qubit. Of course, we're dealing with a qubit that has multiple circulating current states. And so depending on where you set the bias of your QFP, you still get digital information. It doesn't tell you this is 3 and this is 1 and this is 2. It just tells you, okay, if you set your bias here, it'll just tell you, well, it's state 1, 2, 3, or 4. Or if you see the other sign, it was 0, -1, -2, or -3. Or of course, if you set your threshold at a different level, you then kind of can distinguish, oh no, it was below this value or above that value. Okay, so I tell you that so that I can kind of walk you through the signal that we see here from these qubits. So on this kind of x-axis, again, is this kind of this delta bias into this QFP. And if you kind of trace out a line, you kind of see that S curve that I was talking about, where it goes from very high probability down to very low probability. And on the y-axis, what you see is there is a control protocol that didn't go into the details of that can kind of set your current mirror into one of its circulating current states. And then what happens is and you can kind of see that, you know, if you set it into one of those states, you kind of see the place at which this switch from high to low changes. Now, if you go to very high circulating current states, it then decays down to some of the lower circulating current states. And that's what we kind of see here. So one of the things about the current mirrors that we are developing is that each of these junctions is formed out of a compound junction. And so that allows us to run a global bias line that simultaneously biases all of those junctions at once. And so it kind of allows you to lower all of the potential energies of your qubit and encourage this type of vortex hopping of your device. And so what we see here is we've just kind of modulated, lowered all those barriers, and what we see is, instead of, when you prepare in the -1 state, instead of relaxing to the global ground state, the 0 state, that -1 state actually relaxes just to the lowest energy state within its parity sector. And so what we're seeing here is direct evidence of ability to kind of tunably, tunable parity metastability in these devices. And it kind of gives us confidence that we have this ability to kind of to turn on, in some sense, large double vortex hopping while suppressing single vortex hopping. And that is the essential physics that we're looking for these devices. To enable the protection. And that kind of, you kind of encode information in the vortex parity, and then you can become suppress sensitivity to environmental noise. So we're developing ideas as to how to turn on couplings. It's a parity coupler, and there's all sorts of fun effects you might see once you get that device working. So I'll just kind of close here with some of the very exciting research. Here, there's great work on 0-pi qubits, which are very related to current mirror qubits. High coherence fluxonium is really interesting. Here's a recent review paper from the Princeton group and collaborators. Here on this slide, what I want to emphasize is some of the work that's come out of Rutgers and UMass Boston is that they've actually managed to engineer quite remarkable offset charge stability. So all this kind of quasi-particle poisoning that's seen extensively in transmons, for instance, you have the famous, if you kind of tune yourself, out of the transmon regime into that charge qubit regime, you kind of see as a function of offset charge bias, you kind of see that famous eye diagram. In this case, you don't see that at all. And how do they get it? It's kind of two things. They do some really interesting stuff with their gap engineering, but that in turn isn't enough. They also kind of, the diffusion of quasi-particles is really impeded by these kind of superinductors, or sometimes other high kinetic inductance traces. And so those two things together allows the researchers to really observe these kind of really remarkable offset charge stabilities. In this case, for two islands simultaneously on the order of 5 minutes. You can really imagine getting in there and doing some really interesting experiments before a quasi-particle comes in there and changes your offset charge by E, which in many devices would just scramble all your protection that you were trying to put in place. All right, so we got great stuff in terms of the simulations that we have in work. I hope this is an area where we can expand our collaborations going forward. It's something that we could really use there are some great tools that are out there in the community, but having making sure that we're aligning our efforts, I think, would be really really exciting. So I will just kind of go to this one and just kind of say thank you very much. I look forward to next time I can meet you all guys in person, the next March meeting, perhaps. Cross our fingers, and stop me in the hallway and say, hey, I saw your talk, and I'd of course love to talk about this stuff.
Well,
further.
if ARO goes on with the plans to have an in-person meeting in the summer, some of us will be there.
Awesome. Yes, of course. Yeah. Any opportunity. I am itching. I have any sort of conferences that are coming up. That are in person. I'm trying to convince my my various managers that it's critical for me to attend this stuff. But certainly that's a key opportunity. Those ARO review meetings are where a lot of
let's go move to see if there's comments, questions from the audience.
Yeah, hi, thanks, David, for the very nice talk. Relevant to my interests are, in the context of what you're talking about, the properties, characteristics of, your materials and qubit devices, technologies, in terms of simulation and finding, quote unquote, the best tech for these sorts of things. What should be modeled? Like what's important for you? What would be useful for you to understand or learn that currently there are limitations on?
Yeah, that's a great question. I would say that some of the most important properties are well characterized noise power spectral densities, and studies of correlated noise is also critical. If muons are coming in and wrecking everything, that's critical to know, for instance. Yeah, I would say that's characterizing noise in these systems really well. Is it Gaussian noise, or are there in critical aspects beyond that? Beyond the 1/f, telegraph noise. All this stuff is important to really be able to match. If you leave us theorists to our own devices, we're going to assume that the noise is white, and we can protect against that. But of course, it's important to meet reality. Yeah.
Okay, thank you.
Any other questions? That's a little bit pushing a little bit more on noise.
Yeah.
How bad is correlated noise for you guys?
So it depends on how it acts. If you have, say like let's say you have some sort of, noise here that's linearly coupling into every qubit simultaneously. Actually, these codes are good at suppressing that. The thing that they do not suppress are your logical operators, which are of course high weight operators, like XXXXX all the way across your device. So high weight operators, they do not protect against. They are linearly sensitive against those. But even if your noise is correlated, in the sense that you're going to get Z noise on all the qubits at the same time, it can be quite resilient against that noise. However, go ahead.
So then if you get many X's sort of close in time, that's bad, and the limit for when it gets bad is set by the distance of your code?
Exactly, yes.
Okay.
Yeah. Yeah, obviously you still, starting with good, even though you are suppressing sensitivity to noise, you are still sensitive to noise.
Yeah.
It
doesn't matter of what level.
Yeah, exactly. It's going to still be critical to suppress noise. Yeah.
No, yeah. I just wanted to know where the limits are.
Yeah, for sure. No, it is, but I agree that it is, studying the, not just, in this error suppressing context, but even, in the more standard kind of conventional approaches to error correction, error that, all these type of correlated noises are critical to understand. And it's one area that, that I think that is great work is taking place.
Okay. Other questions, comments from the audience?
Yeah, how would you prioritize spatial versus temporal noise?
Let's see here. That's a great question. I guess I would say that Oh, yeah. I would say that probably a spatial noise is certainly something that I would love to see research into. For instance, correlated charge noise. There's good studies there. Correlated flux noise. It's the McDermott group, for instance, has been doing great work here. And a lot of times in our models, we kind of want to put per element noise, but a lot of times it's actually the noise tends out to be per loop. And so really kind of understanding the microscopic mechanism of noise and how it couples in, I guess that's where I would also be very excited to learn more. And a lot of times people just say we've measured a noise power spectrum, but getting nice community consensus on what are the the microscopic causes of these noise, I think would also be great. So I get that wasn't a contrast of time versus space necessarily, but yeah.
Gotcha. Thank you very much.
Yeah.
Okay. Any other questions? Then let's virtually thank David. Thank you, David. That was a very good talk.
Thanks, man. Yeah, it was a pleasure. And again, I'm happy to talk. If anybody wants to reach out to me, David has my contact information. I'm not super easy to find on the interwebs. And of course, Northrop Grumman, we're growing all the time. So if you want to even just kind of, consider what it's like, what we'd like to eventually go there in the near term and the far term, just go ahead and reach out and I'd be happy to put you in touch with the right person.
Okay. Thank you, David. And thank you everyone for coming.